Association analysis, you are now entering into the realms of unsupervised learning. Association analysis measures the strength of co-occurrence between two items. The objective of this class of data mining algorithms is not to predict the occurrence of an item, as in classification or regression, but to identify usable patterns in the co-occurrences of the items. Association rules learning is a branch of an unsupervised learning process that discovers hidden patterns in data in the form of easily recognizable rules. It is also called as market basket analysis and is one of the fundamental techniques used by large retailers to uncover the association between items. In other words, it allows retailers to identify the relationship between items which are more frequently bought together. The model outcome of an association analysis can be represented as a set of rules as item A implies item B. This rule indicates that, based on the history of all the transactions, if item A is found in a transaction or a basket, there is a strong propensity of occurrence of item B within the same transaction. Here, item A is the antecedent or premise of the rule and item B is consequent or conclusion of the rule. The antecedent and consequent of the rule can contain more than one item, like item A and item C. In order to mine these kind of rules from the data, you would need to analyze all the previous customer purchase transactions. In a retail business, there would be millions of transactions made in a day with thousands of stock keeping units, which are unique identifiers for a product or an item sold and stocked. Hence, two of the key considerations of association analysis are computational time and resources. Consider a media website like BBC or Yahoo News with categories such as news, sports, weather, travel, and finance. A session or transaction in this example is one visit for the website where the same user accesses content from different categories within a certain session period. Sessions are very much similar to the transactions in a traditional brick and mortar model, and the pages accessed can be related to the items purchased. In case of online news sites, visits to the categories such as news, finance, entertainment, sports, and arts are considered as items. You can collect the data as shown with a list of sessions and media categories accessed during a given session. Our objective in this data mining task is to find associations between the media categories. For association analysis of these media categories, you would need a data set in a particular transaction format. To get started with association analysis, it would be helpful to pivot the data in the format shown here. This binary format indicates the presence or absence of article categories and ignores qualities such as minutes spent viewing or the sequence of access, which can be important in certain sequence analysis. The strength of an association rule is commonly quantified by various measures of a rule. These are support. The support of an item is simply the relative frequency of the occurrence of an item set in the transaction set. In the data set shown in the table, support of news is 5 out of 6 transactions. 5 by 6 is equal to 0.83. Similarly, support of an item set news finance is the co-occurrence of both news and finance in a transaction with respect to all the transactions. Support news is equal to 5 by 6 is equal to 0.83. Support news finance is equal to 4 by 6 is equal to 0.67. The support of a rule is a measure of how all the items in a rule are represented in overall transactions. For example, in the rule news implies sports, news and sports occur in 2 of the 6 transactions, and hence support for the rule news implies sports is 0.33. The support measure for a rule indicates whether a rule is worth considering. Since the support measure favors the items having high occurrence, it uncovers the patterns that are worth taking advantage of and investigating. Confidence. Given two items X and Y, confidence measures the percentage of times that item Y is purchased given that item X was purchased. It measures the likelihood of occurrence of the consequent of the rule out of all the transactions that contain the antecedent of the rule. Confidence provides the reliability measure of the rule. Confidence of the rule X implies Y is calculated by confidence X implies Y is equal to support X union Y divided by support X. In the case of the rule news finance implies sports, the question that the confidence measure answers is, if a transaction has both news and finance, what is the likelihood of seeing sports in it? Confidence news finance implies sports is equal to support news finance sports divided by support news finance is equal to 2 by 6 divided by 4 by 6 is equal to 0.5. Half of the transactions that contain news and finance also contain sports. This means 50% of users who visit the news and finance pages also visit sports pages. Confidence values range from 0 to 1, where 0 indicates that Y is never purchased when X is purchased, and 1 indicates that Y is always purchased whenever X is purchased. Note that the confidence measure is directional and will change if item sets of a rule is swapped. Lift. Though confidence of the rule is widely used, it is difficult to conclude whether a high confidence implies that there is a relationship between two items or they occur together in the same order simply by chance. Such situations can be explained with the help of lift measures. Unlike the confidence metric, whose value may vary depending on the direction, for example, confidence X implies Y may be different from confidence Y implies X. Lift has no direction. This means that the lift XY is always equal to the lift YX. Lift X implies Y is equal to support X union Y divided by support X multiplied by support Y. In the case of our example, lift news finance implies sports is equal to support X union Y divided by support X multiplied by support Y is equal to 0.333 divided by 0.667 multiplied by 0.33 is equal to 1.5. Lift can take the following values. Lift is equal to 1 implies no relationship between X and Y, that is X and Y occur together only by chance. Lift greater than 1 implies that there is a positive relationship between X and Y, that is X and Y occur together more often than random. Lift less than 1 implies that there is a negative relationship between X and Y, that is X and Y occur together less often than random. In the example, lift is the ratio of the observed support of news plus finance and sports with what is expected if news plus finance and sports usage were completely independent. Lift values closer to 1 mean that the antecedent and consequent of the rules are independent and the rule is not interesting. The higher the value of lift, the more interesting the rules are. The process of generating meaningful association rules from the dataset can be broken down into two basic tasks. Finding all frequent item sets. For an association analysis of n items, it is possible to find 2 to the power n minus 1 item sets, excluding the null item set. As the number of items increase, there is an exponential increase in the number of item sets. Hence, it is critical to set a minimal support threshold to discard less frequently occurring item sets in the transaction universe. Extracting rules from frequent item sets. For the data set with n items, it is possible to find 3 to the power n minus 2 to the power n plus 1 rules. This step extracts all the rules with a confidence higher than a minimum confidence threshold. This two-step process generates hundreds of rules even for a small dataset with dozens of items. Hence, it is important to set a reasonable support and confidence threshold to filter out less frequent and less relevant rules in the search space. The generated rules can also be evaluated with support, confidence and lift measures. In terms of computational requirements, finding all the frequent item sets above a support threshold is more expensive than extracting the rules. Fortunately, there are some algorithmic approaches to efficiently find the frequent item sets. The a priori and FP growth algorithms are two of the most popular association analysis algorithms. Here, you will become familiar with the working of a priori algorithm. A priori algorithm is a classical algorithm in data mining. It is used for mining frequent item sets and relevant association rules. It is devised to operate on a database containing a lot of transactions, for instance, items brought by customers in a store. Take another example from the supermarket sphere to understand this. The example considers a few transactions only, whereas in practical situations, data sets contain millions or billions of transactions. The set of item sets is I is equal to onion, potato, burger, milk, beer, and the database consists of 6 transactions. Each transaction is a tuple of zeros and ones, where 0 represents the absence of an item and 1 the presence. An example for a rule in this scenario would be onion potato implies burger, which means that if onion and potato are bought, customers also buy a burger. A key concept in a priori algorithm is the anti-monotonicity of the support measure. It assumes that all subsets of a frequent item set must be frequent. Similarly, for any infrequent item set, all its supersets must be infrequent too. Now, take a look at the intuitive explanation of the algorithm with the help of the example. Before beginning the process, set the support threshold to 50%. That is, only those items are significant for which the support is more than 50%. That is, they should appear in more than 3 transactions. Step 1. Create a frequency table of all the items that occur in all the transactions as shown here. Step 2. You know that only those elements are significant for which the support is greater than or equal to the threshold support. Here, support threshold is 50%. Hence, all those items are significant which occur in more than 3 transactions, and such items are onion O, potato P, burger B and milk M. The table represents the single items that are purchased by the customers frequently. Step 3. The next step is to make all the possible pairs of the significant items, keeping in mind that the order does not matter. That is, AB is same as BA. To do this, take the first item and pair it with all the others such as OP, OB and OM. Similarly, consider the second item and pair it with the preceding items, that is PB and PM. You will be considering only the preceding items because PO same as OP already exists. Therefore, the pairs in the example are OP, OB, OM, PB, PM and BM. Step 4. Now count the occurrences of each pair in all the transactions. Step 5. Again, only those item sets are significant which cross the support threshold, and these are OP, OB, PB and PM. Step 6. Now look for a set of 3 items that are purchased together. Use the item sets found in step 5 and create a set of 3 items. In order to create a set of 3 items, another rule called self-join is required. According to this rule, look for 2 pairs with identical first letter from the item pairs OP, OB, PB and PM. OP and OB, this gives OPB. PB and PM, this gives PBM. Next, find the frequency for these 2 item sets. Applying the threshold rule again, you will find that OPB is the only significant item set. Therefore, the set of 3 items that was purchased most frequently is OPB. The example is a fairly simple one, and mining the frequent item set stopped at 3 items, but in practice there are dozens of items and this process could continue to generate many items. Suppose you got the significant sets with 3 items as OPQ, OPR, OQR, OQS and PQR, and you want to generate the set of 4 items. For this, you need to look at the sets which have common first 2 alphabets. OPQ and OPR give OPQR, OQR and OQS give OQRS. Basically, you have to look for sets which only differ in their last letter or item. Now that you have looked at an example of the functionality of a priori algorithm, learn to formulate the general process. The entire algorithm can be divided into 2 steps. Step 1. Apply minimum support to find all the frequent sets with k items in a database. Step 2. Use the self-join rule to find the frequent sets with k plus 1 items with the help of frequent k item sets. Repeat this process from k is equal to 1 to the point when you are unable to apply the self-join rule. Mining association rules means finding association rules efficiently. This is another task for which you can use the a priori algorithm. For finding association rules, you need to find all the rules that have support greater than the threshold support and confidence greater than the threshold confidence. How to find these? One possible way is brute force, wherein you list all the possible association rules and calculate the support and confidence for each rule. Eliminate the rules that fail the threshold support and confidence. It is computationally very heavy and prohibitive as the number of all the possible association rules increase exponentially with the number of items. Given there are n items in the set I, the total number of possible association rules is 3 to the power n minus 2 to the power n plus 1 plus 1. There is one more way called the two-step approach to find the efficient association rules. The two-step approach includes Step 1. Frequent item set generation. Find those item sets for which the support is greater than the threshold support following the process you have already seen. Step 2. Rule generation. Create rules from each frequent item set using the binary partition of frequent item sets and look for the ones with high confidence. These rules are called candidate rules. Refer to the previous example to get an efficient association rule. In the example, OPB was the frequent item set, which means step 1 has already been taken care of. Now come to step 2. All the possible rules using OPB are OP implies B, OB implies P, PB implies O, B implies OP, P implies OB, and O implies PB. Find measures like confidence and lift for these rules, and based on these parameters the most applicable rules will be considered as the frequent item sets. These rules should be further evaluated for rational validity to determine if a useful relationship was uncovered, if there was an occurrence by chance, or if the rule confirms a known intuitive relationship. If X is a frequent item set with k elements, then there are 2 to the power k minus 2 candidate association rules.